Yes.
Okay, so next we have Yuchao Chen from Cornell University, who's going to tell us about residential segregation.
Hi, can you guys hear me?
Yes.
Cool. So I'll be telling you today about predicting residential segregation using statistical physics approaches. So what you see on the left here is the map of Denver, and the different colors here, oops. Oh, sorry. Oh. And the different colors here represent different races or ethnicities. So we've developed a tool that allows us to extract spatial and social preferences by looking at these data alone. And in addition, if we know how the total population of the city changes at the future time, we can predict the racial composition for every block in the city. And this is a completely new type of prediction that may inform policymaking or city planning. So today I'll show you how well this tool works on the simulated data as our first test. And to start, I'll just show you how we extract spatial and social preferences. The tool we use is called the density functional fluctuation theory. And it is inspired from density functional theory, which is used to describe, so the main idea there is it relates energy of a collection of electrons with electron density. So with a similar concept and using tools of statistical physics, we can make a similar connection between population density fluctuations with an energy-like description of the crowd. So to give you an idea of what these things are, here's a toy example of a beachside town. And if you look at those blue dots, these represent people that want to live closer to the beach. And if we look at how the number of people fluctuates inside those blocks over time, we can extract those probability distributions of number of people in those blocks. By looking at the means of these distributions, DFFT extracts a potential-like number for each block. So a block with low potential means that the block has a higher mean number of people, which means that it is spatially preferred. And by looking at the shapes of those distributions, DFFT extracts a function called frustration. So this function tells us the level of frustration in the block as we put more or less people into the block. And this function gives social preference information. And to better explain what this function does, here are some examples. When there's no interaction, we get a Poisson distribution, and the frustration we extract is constant, doesn't depend on the number of people as we expected. When we have attractive interaction, we have a bimodal distribution, which gives a frustration that curves down. And it tells us that people prefer blocks that are filled. When we have repulsive interaction, we get a narrowly peaked distribution, and the frustration curves up. This tells us that people prefer blocks that are empty. So now I'll show you how exactly we extract potential and frustration from these distributions according to this equation. So the DFFT tells us the probability distribution for each block is something like it's like a Boltzmann-like distribution, where in the exponential we have an energy-like term, h of b, and the constant in the linear term here gives us the potential for that block. And all the higher order terms are captured in this frustration. And note that this is a single frustration that works for all these different blocks. This description has been tested experimentally on a system walking fruit flies, and it worked pretty well there. And also it has been shown that it works for generic crowd, generic model of interacting crowds. So in order to describe racial segregation, we need to extend this theory to multiple components. So for instance, if we have a city with red and blue people, then the probability distribution now becomes a joint distribution of red and blue people. And then the potential we extract now has two parts. The first part is the potential for red people for each block, and the potential for blue people for each block. And when we look at the frustration, it becomes a function of two variables, the number red and number blue. And the analytical expression looks similar to what we had before. Now let's apply this to the Shanling simulation of segregation. In this simulation, we have red and blue people in this city, and they move with some preference. So red and blue people both prefer to move to locations that are surrounded by people of its own type. And red people prefers to move to the west, and blue people prefers to move to the south. And if we let the system evolve over time, we're going to reach some steady state that looks like this. And now we do the trick of coarse graining it into many blocks and watch the probability distributions. For instance, for this block, the probability distribution tells us that this block is, most of the time we see it to be filled with red people, but little blue people. And similarly, we get the distributions for the rest of the blocks, and there are 25 of them. And from these distributions, and with this equation, we can extract a potential of red, which tells us that red people prefers the west of the city, and the potential for red telling us blue people like the south of the city, and frustration. And this frustration tells us that the level of frustration in a block is low when the block is filled with mostly blue or mostly red, but the frustration is high when we have an equal number of red and blue. And this frustration is telling us that there is segregation going on because red and blue people don't want to mix with each other. So by looking at data alone, we are able to extract basically all the information there is from the Schelling simulation. Now let's see if we can use these extracted preferences to predict the future population distribution as we impose a change of number. The change is as follows. We first take our initial steady state, and at time t equal to 0, I remove 60 red agents and introduce 60 blue agents to get this perturbed state. And then over time, this state is going to evolve to some new steady state. And it is this time, it's the time evolution of the population from the perturbed state to the new steady state that we want to predict. So in the prediction, we take our perturbed state. Instead of focusing on the individuals like the Schelling simulation does, we here only focus on the number, the density of people in each block. And to make prediction, we run a Monte Carlo simulation where at each step, we first randomly select a chunk of density, which happens to be in block I, and then randomly select block J. And the chunk of density will move from block I to block J with a certain probability that depends on the changing energy of the system. And the energy, as I showed you earlier, depends on the extracted potential and the frustration. So if there's an increase in overall energy, the move is less likely to happen. And as a side note, this prediction is inspired from time-dependent density functional theory. So let's see how this prediction does. So here I'm showing you the average red number and average blue number for each block as they evolve over time. And you can see the FFT predicts red to migrate to the north and the blue to migrate to this part, and they eventually settle down in this kind of configuration. And we can now compare that with what we actually observed from the Schelling simulation. And indeed, the time evolution agrees pretty well, and also the final steady state agrees pretty well. So we can also plot how the average number of red and average number of blue evolve together in this joint number space. So here I'm showing you the predicted trajectories for 3 blocks. What's particularly interesting is the northeast block, where as it evolves from the perturbed state to the final state, its trajectory has that interesting kink. So is this feature artificial? So when we look at the observed trajectory, we see that indeed there is this kink. So this feature really shows the predictive power of the DFFT. So in sum, what I showed you today is by observing data from a Schelling simulation, DFFT is able to extract spatial and social preferences, and using those extracted preferences, it's able to accurately predict the time evolution of spatial distribution of people. And in the future, we want to apply the same tool to study real data and test with real data. So for instance, we can look at the census data in 2010 in Denver, and then predict the spatial the population distribution of people in 2020 and see if it agrees with the 2020 census data. We already have some preliminary results on down on the county level, so it's at a much larger scale. And we're looking at counties in the entire United States. So the extracted spatial preference and the social preference look like these. So the potentials tell us white prefers the north and black prefers the south. And this frustration tells us the level of frustration in the county is low when the county is filled with white or when it's filled with non-white. And this is telling us there is segregation. And can we predict the 2020? We'll see about that later this year when 2020 census data comes out. And that's it. Thank you.
Thank you. Okay, we have a question from Ritvika.
Hi, you can also just call me Ritu. That's what I usually go by.
Okay.
I just, really interesting talk. I just wanted to ask if there are any insights that you can draw from your model about interventions to combat segregation.
We think it's possible. So first, we're physicists, so we don't really deal with those issues. We only provide the predictive tool that will potentially allow policymakers to make decisions or allow other researchers like social scientists to, for instance, describe segregation and study how previous tools to deal with segregation has affected segregation. So these are the things we provide. And we don't really have an answer to that part of the story.
I guess, I'm sorry, I should have rephrased it better. Like, theoretically, what factors do you think would decrease frustration?
Theoretically.
Mm-hmm.
So what we're giving here is an effective description of crowd. So here it will be like, if red people and blue people don't want to stay with people of their own kind, then certainly frustration will go down. Mm-hmm. Or there is the spatial preference. If there's really no difference, then of course segregation is also less. Okay. But how do these factors relate to the reality? That's not a question we can answer. And,
of course, yeah. Thank you so much. It's very cool stuff.
Thank you.
Yes, indeed. Thank you very much. I think we're going to move on to the next speaker, who